So we're gonna have like a new session today, and Thomas asked me to chair that session. So we are very happy of having Joris Mooij that's gonna present causal inference from combined observational and interventional data. So Joris, the floor is yours, and anytime that we have a question, I will let you know, me or Thomas, and the person will ask the question directly. Thank you very much.
Okay, thanks a lot. It's sad that I couldn't be there with you physically, but at least I'm very happy that I can participate virtually. And I would like to thank the organizers for organizing a very interesting workshop. The work I'm going to present is joint work with Maximilian Ilse, Patrick Fauré, and Max Welling. We're all from the University of Amsterdam. Before I continue, let me check. Can you hear me well enough?
Yes.
Yes. Okay, thanks. So the motivation behind this work comes from questions like the following. For example, how well does a booster vaccination protect against COVID? Which I remember was a very relevant question a few months ago. Perhaps now it's a little less relevant. But anyway, this is a simple question to pose, but it's not so easy to answer. Of course, we can make use of the gold standard in principle using interventional data. So we could set up a randomized controlled trial and use that to estimate the causal effect of the booster vaccination. But it could be unfeasible to set up such a randomized controlled trial because perhaps you want to immediately decide who is going to get the booster and not wait for some study that might take a year. Could also be unethical. So the question is, can we make use of observational data instead, perhaps? Well, of course, the well-known problem here is that of confounding. For example, there can be if many persons that decide to get a booster vaccination also take other measures, so it's perhaps the more cautious persons that decide to get a booster, then we don't know whether the difference in the probability to get affected that we see is due to the booster or due to other things. So a standard solution in a way is to try to observe all potential confounders. For example, age could be one of those confounders, and try to adjust for them. But of course, how do you know whether you have observed all potential confounders? And in practice, there will always be some remaining unobserved confounding. What about it? So in this work, we basically propose a principled approach. We're not going to solve this question above, but we do propose a principled approach to obtaining more accurate estimates of causal effects by combining observational and interventional data. And the estimates, we hope that they are more accurate than what you would get if you would only make use of the interventional data, even if there's unobserved confounding. So the main technical tool here will be that of what we call a causal reduction. So I will first explain what we mean by that. The high-level idea is the following. Take some causal model, could be of your favorite type. For example, in this presentation, I will be making use of causal base nets, but you can do the same construction for other causal models. And suppose it has an observed variable x, a treatment variable, y, an outcome variable, and suppose it has latent confounders. There could be an arbitrary number of them, so k unobserved common causes of x and y that are explicitly accounted for in the model. Or alternatively, you could start from a joint distribution of potential outcomes, x, y, and the potential outcomes for y if we set x to a certain value, small x, that satisfy the consistency assumption. Then our goal would be to get in a way, the most parsimonious parameterization for jointly modeling both the observational distribution, so the joint distribution in the observational regime of treatment and outcome, and the interventional distributions that I will denote using the do operator. So as the distribution of y if we do x. And this is just the distribution of the potential outcome y of x. So what we will do is define a causal reduction that takes a causal model as input, and it modifies this, so it outputs another causal model, and that is interventionally equivalent. So it will preserve the observational distribution and the interventional distributions, but often it has a smaller latent variable space. How do we do this? Well, it's a series of 4 steps. In the first step, suppose we have this causal Bayesian network that I sketched here. It could have a very complicated latent structure, but all these z's are latent common causes of x and y, treatment and outcome. The first step is just to combine all these latent confounders z1 to zk into one combined confounder z that has all these as components. That's quite a boring step, but at least it makes, well, it gives you a cleaner picture on the right-hand side. The second step is that we introduce a latent copy w of x. So here we add this w variable between z and x. We assume it to be latent, and basically it must have the same value as x. So the distribution of x given w, it's just a point, well, a delta kernel. And so there's this deterministic relationship that I indicate in the graph by using these double circles. So x is because there's a double circle around x, it's a deterministic function of its parents. Now, in the next step, this is perhaps the most exciting one, we change the directionality of the arrow between w and z. And that is basically just a refactorization. First, we had the joint distribution of z and w factorized in one way, but we can turn it around, as you see on the bottom of the slide. Unfortunately, I don't have a mouse pointer to illustrate things, but I hope this is clear. This, well, of course, preserves the joint distribution of w and z in our model. The last step is that we can now integrate over z. So we can marginalize z out, and that gives us the model on the bottom, where we have this new kernel, Markov kernel q of y, and we have this q of w, which is actually the same as the observational distribution of x, the treatment. Okay, so a few simple steps, and each step basically preserves the observational distribution and the interventional distributions. And we have ended up with a causal model with a single confounder w, that takes values in the same space as the treatment. So this is where we may have really reduced the size of the latent space. Observationally, in the observational regime, x has the same value as w, and our model parameters are now the marginal distribution of the treatment in the observational regime and this Markov kernel q of y. If there are no questions about this, then I will continue. Otherwise, perhaps I can clarify something. No, then I will just continue.
Joris, there is a quick question.
There is a question.
I think it's quick.
Can you go back to previous slide?
Yes.
So now, why do you have an arrow from w to y if w is equal to x and x already goes to y? Maybe this illustrates the fact that I did not understand.
Yeah, okay, I kind of understand your question, but I need this because there can be a difference. I mean, if I intervene on x to set x to a certain value, small x, okay, then things are different. I haven't illustrated this graphically, I only gave you the formula for P of y given do x. But basically, to be able to represent both the observational distribution and the interventional distributions at the same time, I need that. Does it answer your question?
It's okay with the answer, I guess.
Okay. Okay. So we.
Sorry.
There's more.
I mean, I understood the answer you gave from a technical point of view. I'm just trying to understand it a bit from a physical point of view. So the idea is that if I don't intervene on X, for sure X will be the same value as W. But I can intervene on X and set it to some other value which won't change W, right?
Mm-hmm.
So, I mean, then you'll get a different interventional marginals, blah, blah, blah. But can you give me an example of a situation like that? I mean, I just can't think of any plausible situation that would have that structure, that on the one hand, W completely determines X, but on the other hand, I can intervene on X and not affect W at all.
So basically, W just represents the value that X would have had observationally. You can think about it like that. And to be able to represent the confounding, that has to interact also with Y. So Y must depend on, I mean, there was this latent confounder, right, that gave rise in our original model. We have actually all these latent confounders that could give rise to a dependence between X and Y, even if there's no, even if there would be no effect of X on Y. So if the arrow from X to Y is not there. And that is basically also why we need here the arrow from W to Y and from W to X to realize that dependency. Even if there would be no direct effect from X to Y. Does that help?
That helps.
Okay, great.
So you could continue.
Okay, now often we also have some observed confounders. For example, H in the booster vaccination example might be available as a measured confounder. We can then do the same, basically the same derivation in the presence of these observed confounders C. I won't go into detail here, but the four diagrams illustrate the same series of steps as before, but now we also have this variable C. And this basically gives a causal reduction that preserves the conditional distribution of treatment and outcome given C, and also the interventional distribution of outcome given that we intervene on treatment and conditional on C. But it doesn't, perhaps you might have expected that it preserves all the interventional distributions in the model, but here I would like to point out that it doesn't preserve all of them. But the two interesting ones are preserved. Okay, let's move on to causal inference, and let's start with considering the discrete case. So the reduced causal model, if all the variables are discrete, these are the same formulas as before, but now with sums instead of integrals. And if you look at the formulas, then the interventional distribution of y given do x, that's the sum over w of a product of two factors. And we can split it into one term where w equals x, and the remaining w's that are unequal to x. And the term where w equals x, that is actually the same one that ends up in the observational joint density of x and y. And now in this remaining sum over the other values of w unequal to x, we can now simply bound the factors that are there because they have to be between 0 and 1. And then we obtain with this bound that is written there. And this is known as these are known as the natural bounds by Mensky and Nagin, 1998. So this is not new, but perhaps this is a nice derivation of these bounds. And you also can do a similar derivation in the presence of observed confounders C. Now, how can we estimate the causal effect from data? Well, we can do maximum likelihood estimation in this case, also from combined data. So let us first choose parameterization. We can choose these parameters, the phi and the theta parameters for the observational. They encode the observational distribution, and the psi parameters for the interventional distributions. And they're, of course, subject to non-negativity and normalization constraints. But in addition, they have to satisfy this natural bound, as we just saw. Now, suppose we have observational data and interventional data, then we can just write down the total log likelihood of the data. And it nicely splits into an observational and an interventional term, where the observational term only depends on the observational data and observational parameters. And the interventional term only depends on the interventional data, interventional parameters. But the parameters are actually coupled through these natural bounds. So there is some interaction between the two terms going on. Now, I don't know of a closed form solution for this problem, but you can always optimize it numerically. But we can gain some intuition of what it's doing by considering the limits where the observational sample size tends to infinity, but we keep the number of interventional samples fixed, because there the observational term will dominate the log likelihoods. So we will just end up with the standard maximum likelihood estimators for the phi and theta parameters that we would have got, that we get from only looking at the observational data. And then we can make use of this natural bound, which is now has become a bound on the psi parameters. And if the standard maximum likelihood estimator for the interventional data satisfies the bound, then that will be our estimator for the psi parameters. But if it violates the bound, then basically the bound serves as kind of it clips the value of this estimator. And in that way, we can end up with a more accurate estimate. So here's an example to get a feeling for how this can be exploited. So we consider an extreme value for the probability of treatment in the observational data. And this could correspond with, for example, a treatment with a new vaccine, because then we may have lots of observational data lying around, but in the observational regime, everyone would be untreated simply because it's a new vaccine that hasn't been used before. So from the observational data, we can get an accurate estimate of, for example, the conditional probability of remaining healthy given that you're not treated. On the other hand, there might be a small randomized controlled trial where we have two groups, a treatment group and a no treatment group consisting of 100 persons each. And from that, we can estimate these interventional quantities, but they will have large confidence intervals. So the difference that we might see in the randomized controlled trials might not be significant. Now, because in the observational setting, everyone was untreated, the bound actually becomes sharp. And this quantity in red, the probability of y given that we that we intervene to give no treatment, is actually equal to the marginal probability in the observational regime of the outcome. So we can also estimate that much more accurately. And then if you do that, you find in this case for these numbers that there might be that there is a significant effect of the vaccine on the outcome. And you also realize, yes, question? Mm-hmm.
Just a quick question, that when you're saying that it's a randomized trial there, you mean it has to be a random sample that is then randomized? I mean, in reality, you might worry that people that are volunteering to be in the randomized trial are not like the people in the observational study. Yeah,
so it's very, the underlying assumption here is that the two populations in the observational study and in the randomized controlled trial are the same. or well, not the same, but are kind of, they have the same features. So that is indeed an important assumption here. But remember that we can also, in the presence of the covariates, we can also perhaps look at subpopulations that are the same when we do this. So under that assumption, we can get this improvement in the estimator. But you can also see that perhaps it would have made sense to set up the randomized controlled trial differently, namely to assign everyone just to the treatment group, because then you get also a more accurate estimate for P of y given do x equals 1. And that gives you a more accurate estimate of the average treatment effect. What can we do in the continuous case? So actually, I don't know if this idea is new, or if anyone is actually already doing this. But I thought it's a nice way to exploit these bounds, and could be practically relevant actually. But let's move on to the continuous case now. How much time do I have? 15 more minutes. Sorry?
27.
Yes. So in case treatment and outcome are continuous, for example, if we are estimating dose response curves or even quantile dose response curves, then we can make use of this reparameterization trick to parameterize Markov kernels by deterministic functions. So also this is a fairly standard trick. Graphically, it looks like this. If we have this Markov kernel, P of y given x, then we can represent it as a y being a deterministic function of x and some independent noise variable u, where we can assume that u has a multivariate Gaussian distribution in the same space as y.
Joris?
Yes?
Just to clarify, you have 17 minutes, sorry.
17, okay, thanks. So we can, so on the top left, you see basically our reduced causal model, and we can now use this reparameterization trick first on W. So we turn W into a deterministic function of C and some independent noise variable U. Then we can actually integrate out or even substitute out the W from the model. We end up with a third graph on top. And then finally, we can apply the reparameterization trick to Y to write it as a function of its parents C and X and a new noise variable V that is independent of U and C and X. And then we end up with this structural causal model parameterization, and that is written here. So I guess that is, if you're familiar with structural causal models, then I guess that should be clear what is going on here. Now, the next step, if we want to do causal inference, it would be to pick the functions f and g in a convenient function class. So basically, we have kind of used the freedom in choosing the functions f and g to already fix the distribution of the noise variables u and v. So we don't have to infer the distribution of u and v from the data. We just have to infer these functions f and g. So we can pick them in some function class. For example, we can assume them to be linear, and that will be the next slide, what the next slide is about. Or we can look at nonlinear functions here, and that will then be the next step after looking at the linear case. And we can then simply, again, optimize the total log likelihoods of these functions f and g. Okay, so let's first look at the linear case. Here we can actually derive also some constraints. So this would be kind of a Linear-Gaussian analog of the natural bounds. So suppose we have a Linear-Gaussian structural causal model or structural equation model, and it has these two variables, x and y. Y is not an ancestor of x. Then we can model the observational and the interventional distributions kind of naively with using these parameters, where we might think that they are independent objects. But by making use of the causal reduction, you can see that the two constraints here at the bottom actually must hold. So there are constraints between the parameters. These are now equality constraints. I also don't know really, so to the best of my knowledge, these are also new constraints. We haven't really pursued what one can do with them because we wanted to move on with the more realistic nonlinear models where we made use of normalizing flows. So perhaps going back to these equations here, normalizing flows, in case you haven't heard of them, they come from the deep learning, neural network learning communities, and they are basically function classes that have some nice properties. So here, if you look at this equation, x is f of c comma u, then you can think about this as being a change of variables from u to x that also depends on c. So conditional on c, we have a change of variables from u to x. And if you then calculate the density of x, conditional on c, you'll get things like the Jacobian of f and the inverse, perhaps. So the nice properties of normalizing flows are that you can easily calculate their inverses and the Jacobian and their inverse Jacobian. So basically that allows you to easily do maximum likelihood with these functions. And also, well, the neural network people have tried to make these function classes as flexible as possible so that you try to, in a way, be as, that you basically can try modeling anything with it. So that's something we just used. And here's what we got. So this takes a little effort to explain what you see here. On the top left, you see samples from the true model. The true model was not picked to be in the modeling class that we use for estimating it. And the blue samples, the blue data points, the blue dots here are from the observational distribution, and the yellow ones are from the interventional distributions. So you can see that there is a difference between the two. So there's some confounding in the observational regime. Now on the top right, you see what we get if you use only 50 interventional samples. So the yellow dots, we take 50 of them randomly, and we train the model. And then we sample from the model again. Then we have reconstructed the interventional density, interventional distributions in the way that you see in the top right scatter plot. So this is not a perfect reconstruction, but it's a reasonable one, perhaps. But what happens now if we also make use of the observational data, so the blue dots? So if we also use 1,000 observational samples and jointly train from these 1,000 observational samples and the 50 interventional samples, then we end up with the reconstruction that you see in the bottom left. And if you look at the yellow dots there, then this looks like a better reconstruction of what you see in the true model than if we don't use the observational data. So, well, this is one example. So this is not yet a proof that this always works. In the paper, we give 10 of these examples, so that's still not a proof. We also try to quantify how much one can gain here. So, but what we did was we used the interventional log likelihood as a loss function, and we found that basically, if you're allowed to make use of additional observational samples during training, then you can basically reduce the number of interventional samples that you need by a factor of 2, roughly, without sacrificing the accuracy of your reconstruction. So that is also, I think, quite promising, even though we don't really understand what this method is doing. It's also a bit of a black box. But this also looks quite promising, I think. So the contributions in this work is that we propose this technique of causal reduction that may give you a more parsimonious parameterization while preserving observational and interventional distributions, at least for this setting of treatment and one outcome variable. And we use this to derive constraints between the parameters in several cases, and to motivate certain causal effect estimators from combined data. And well, to conclude, and perhaps some food for discussion, I hope to have convinced you that causal inference may actually benefit from the presence of confounded observational data without making very strong assumptions. Somehow it seems as if the causal reduction is the opposite of the causal inflation technique, because here we try to reduce the latent space, whereas in causal inflation you try to blow it up. I'm not sure if there's more to it than this this observation, but I found it interesting. Now, since this is also a workshop about quantum physics and perhaps bell-type inequalities, I was wondering in which way the observable constraints that we find here due to latent confounding are related to, say, the Clauser-Horn-Shimoni-Holt inequalities. Of course, we are looking at a simpler setting, so we have only one treatment and one outcome variable, whereas in the bell-type inequalities, you typically have 2 treatments and 2 outcomes. But I'm not really an expert on that literature, so perhaps there's a relationship that I'm not unaware of. I was also wondering in which way, well, whether quantum mechanics allows for a violation of the natural bounds, perhaps, and if there are quantum natural bounds. So perhaps if you have some ideas about this, then I'd be happy to hear your thoughts on this. And well, anything I have left out of the presentation, you can read that in our preprint. So thanks a lot for your attention.
Joris.
Any questions?
Yes.
Comments? Yes.
Hi, Joris. It's Robin here.
Hi, Robin.
Talk. So presumably you could have done that with a swig, right? You could have split the node X in a swig-like way and done everything you did.
I guess so. At some point, I also realized that the construction is very swig-like, but I'm not sure in which way this gains you anything, this insight.
Sure.
It's
and
not
then
entirely clear to me.
I guess the other thing is, I don't know if you know, but people in like, you know, who do randomized trials, they actually do use, you know, general populations as control groups.
In the way that I presented here? Okay, so that's great then. Then we have been reinventing the wheel without knowing, but it's good to know it. So do you have a pointer to a paper where this is written down?
Not off the top of my head, but I don't suppose it would be hard to find.
Okay, but you
like
know it's actually being
control group or something, then you probably would find it.
Okay, yeah, thanks.
So now if you take the Bell scenario and you do the same, I guess that you will have A, which is a deterministic function of you call it the treatment X, right? So A is the outcome, one of the 2 outcomes. Mm-hmm. So it would be a deterministic function of the treatment and the latent variable, right? If you use your technique in the Bell scenario.
So, in the Bell scenario. So y will be a deterministic function, yeah, of x and this w, indeed.
So okay, for sure, this in quantum mechanics you are not allowed to do. So your technique is not, I guess, right, is not valid for quantum mechanics, and you may find Bell inequalities like this.
So it's not valid in quantum mechanics, you're saying?
So in quantum mechanics, what happens is really this output A is non-deterministic, and you cannot imagine it as some hidden determinicity somewhere, right? It's really attached to what is quantum mechanics. This A is fundamentally random.
Right, so you can't use the same technique here, but you can still wonder whether you have some kind of bounds in quantum mechanics, similar to the natural bounds, or are you claiming that
I would not be surprised that you are finding Bell inequality in the Bell scenario with your technique, because okay, you really have a somehow, if you start to assume that it's deterministic, then it becomes classical information. But okay, it's not clear for me how to write it down, but I would not be surprised that you exactly obtain a CHSH, for instance.
Okay, but have people looked into a kind of a CHSH inequality if you only have one treatment and one outcome?
So Eli is saying that I'm wrong, so maybe, okay. This has to be worked out.
Okay.
Okay, maybe. But I think we can get CHCH and CHSH equation inequality with a treatment, a binary treatment, and the binary outcome.
You can, you think? Okay.
Yeah, I think this is definitely worth a longer follow-up conversation. To my mind, although determinism was used in this particular proof, it wasn't the critical aspect, right? The factorization into kernels and the joint distribution over the kernels, as Robin was saying, you could do this with a swig, and all of that logic is quantum valid, the distributions over the kernels. And so I think these natural bounds, in fact, are exactly the same in quantum theory. And it's only if we sort of were to use the non-natural bounds, the one that, like the Balkian Pearl bounds, that we start to see a difference. But this is a longer conversation.
Okay. Thanks for sharing your thoughts on this.
So just one follow-up question that I missed, that in the first two settings you had this restriction relating the observational and interventional models, and then you went, when you went to normalized flow.
Which slide? Sorry, which slide?
I mean, in the beginning you had these constraints relating the observational and interventional distributions, but then when you're optimizing the normalized flows, are those just sort of automatically built in, or how is it? It seemed like you didn't.
Yeah, so that's exactly a thing that puzzles me, or perhaps I got some more insights very recently. I believe that these natural bounds, like they're written here, they are informative for discrete variables, but if in the continuous setting, I think they become completely non-informative, the bounds. So I'm not sure exactly what is going on in that sense, but I think it has to do with regularization and with smoothness assumptions. So perhaps that's an explanation why we seem to get better estimates, because in our normalizing flow parameterization, which is, where is it? Here, we regularize the functions f and g to have a certain smoothness in the end. And perhaps that's what the observational data is mainly used for, to sort of get a good estimate of how smooth f and g must be. And then we can use the interventional data to more completely estimate this function g, but already starting with a good smoothness. So that's right now my conjecture of what's going on here. But in terms of bounds, I haven't been able to derive any bound in the continuous setting.
It's interesting because you could have the intuition. I mean, if you could think about the U's as taking U's and V's taking continuous values, but it really only matters which side you are of some threshold. I mean, maybe that would violate your smoothness assumptions going in there. But anyway.
Yeah. So far, I don't know exactly. It's bothering me a bit that I can't prove anything here, while it seems to work quite well.
Yeah, just to follow up on that, you were thinking about the natural bond and the continuity, but I think the issue is the discreteness of X, not necessarily Y, because even if Y is continuous, you could construct the natural bond in that. I think the issue why you are not able to construct the natural bond is when X is continuous, right?
Yeah, that's true. Yeah, that's exactly the case where it's. I think there's no bound actually, if you don't assume any kind of smoothness.
Yes. So there is an interesting paper in Biometrica from Florian Gonzalez that tried to justify why you do not have this when X is continuous.
Okay, yeah, I think I even found a proof today of this, but but perhaps it's already in that paper then. Thanks for the pointer. So it wouldn't surprise me at all. Yeah. So it's interesting in the sense that if you don't assume smoothness, I think that the observational and the interventional distribution in this continuous setting are variationally independent objects. But still, completely ignoring any kind of smoothness is also perhaps rather drastic.
I can't hear what's going on in the room, but
Okay, but you could speak directly.
okay. I assume I just had a quick comment about your question concerning quantum analogs of the natural bound. It's if you ask a kind of different question, which seems to be of the same flavor. So there's these, classical bounds. Like if you're in the instrumental scenario, you can bound the average causal effect in terms of observational data, and so there has been a paper written about if I replace the latent classical variable in the instrumental scenario with a quantum source, so it becomes the quantum version of the instrumental scenario, do the bounds on the average causal effect change? And the answer in that situation is yes, they do. So it's a similar flavor of question to yours, but in this there has been some previous work that in that sense, the sort of relation between the interventional and the observational can be different in certain circumstances in the quantum realm. Okay,
if you could, if you know which paper it is, and you could.
It's a paper, Rafael Chavez and collaborators. I'll send you an email.
Okay, great, thanks.
Do you have more questions? So maybe let's thank Joris for the very nice presentation. Thank you very much. I think we have a break. Now it's gonna be 5 minutes.